Today we will discuss elliptic solutions of another hierarchy of KP type. It is called BKP. B comes from classification of Lie algebras. There are types A, B, C, D, and some E. So KP hierarchy exists in type A, which is the hierarchy that we considered, B, C, and D. We will not discuss this, but I will give some details on the B type. There is some underlying symmetries of the hierarchies which form infinite dimensional algebras of these types. And BKP hierarchy can be considered as a sub-hierarchy of KP such that the following constraint is satisfied. So we take Lux operator, which is a pseudo-differential operator, some non-commutative Laurent series in the differential operator. And L DAG is conjugated operator, which means the symbol means that conjugation of such operator is, we should read from right to left, take derivative with minus sign, and so this is the rule. And the constraint is that the following constraint. This constraint is destroyed by flows with even times and is preserved by flows in odd times. So to define this hierarchy, we should fix even times, for example, set them to be 0, and consider dynamics only in these times. So the set of independent variables is T1, T3, T5, and so on. And if you restrict them in this way, then there is a subset of all solutions to the KP hierarchy such that if you fix even times in this way and consider dynamics in odd times, you get a solution of BKP hierarchy. But we will not need the full theory, the theory of the hierarchy. We will restrict ourselves to just the first equation and consider its elliptic solutions and dynamics of poles. So the BKP is a system of two equations, a system of two equations for two functions, x t1 and t3, and another function w of x t1, t3. And the system is as follows. Prime means derivative in x. This is partial derivative in t3. We need actually x is t1, then we need the next two times, t3 and t5. Fifth derivative. Rather complicated system, and in principle you can exclude w and pass to another dependent variable, which is integral of u. Then the system can be written as a single equation for this u. This system is a compatibility condition for follows from the Zakharov-Shabat equation for some differential operators, where B3 is a third order operator, it is important that the constant term is absent. So this operator kills constant functions. And B5 is a fifth order operator. And again, the constant term is 0. If you substitute them into this equation, you get this system. This Zakharov-Shabat equation is compatibility condition for the linear equations for a function psi. If you make the following substitutions, introduce some function tau, which is a tau function, and make the substitutions, then the first equation becomes identity, and the second equation becomes bilinear in this function tau. It can be written in Hirota form, but we don't need it. And the psi function, which enters here, can be written in terms of the tau function in the following way. Sum over odd numbers Z is spectral parameter, and so on, divided by tau. So we are interested in elliptic solutions which are with some, so the tau function for elliptic solutions as a function of T3 is what is called elliptic polynomial. So it is a product of Weierstrass sigma functions with some poles which depend on all times, but we fix all higher times and consider the dependence in T3 only, and denote it just as T for simplicity. Then, if you make such ansatz for tau function, then U becomes, U has the following form. It is a sum of Weierstrass P functions. According to the Kricchever method, we should consider the linear equation, the first one with the operator B3. And with this coefficient U, so it is a double periodic function, and it is natural to find solutions among double block functions. So we make the familiar ansatz as a linear combination of Lamé-Hermite functions. The same ansatz as for Calogero-Moser model, and we should substitute it in this equation. If you do so, you get some complicated expression in which there are poles at the points x, when x is equal to xi. There are poles. The highest order pole is 4. Then there are third order poles, second order poles, and simple poles. I will not show you all details. It's rather complicated calculation, but you can see that this high fourth and third order poles cancel identically. And we need to cancel only these poles. This leads to a system of equations for this coefficients Ci in much similar way as it was for a Calogero-Moser case. But now the calculations are more difficult. And the result can be written in the matrix form. We introduce two matrices which depend on spectral parameter lambda and another spectral parameter z, which comes from here. And the system is, again, we introduce the vector C with these components. And then the system has the following form. Let me introduce the following matrices. A, which is off-diagonal matrix with zeros on the main diagonal. I will not write the second argument. Phi prime is derivative in x, in the first argument. We need also the second derivative. So these are off-diagonal matrices, And there are two diagonal matrices. And D prime. Using these matrices, we can represent these L and M in explicit form. And also, as usual, X is diagonal matrix with coordinates on the main diagonal. Then the L matrix can be written in the following way. I is identity matrix. However, there is no lax representation for this system, similar to what we observed when discussed deformed Rusinard-Schneider system. Here also we have Monakov's triple representation rather than lax. And this is not just an occasion, but in fact, the system which we will obtain here can be obtained as a limit eta. You remember there was parameter eta in Rusinard-Schneider systems. When eta tends to 0 is in a deformed Rusinard-Schneider system, we will obtain the system which we discuss now. However, this is a rather tricky limit. In fact, there are several different limits, and this is one of them, not the most simple one. The following identity can be proved, but the proof is not easy. Using these matrices, you can try to calculate this combination. For Lux representation, it was 0. But now it is not 0, but on the right-hand side, we have the following expression. Let me call lambda this combination. This D 3 primes is similar to this with third derivative. So it is this is identity. If you substitute the matrices, all these matrices here, you get identity. So it's just algebraic identity. However, it is not not that a simple procedure to prove it. The proof is rather complicated. I will omit it because it's not easy to show it on the blackboard. In the notes, which will appear on the site, there will be some main points of this proof will be written, so you will be able to see. And in fact, we have the following Monakov's triple representation. This is not 0, but on the right-hand side, we have such matrix. And this is the condition of compatibility of this linear system of equations. If you compare this identity with the Monakov's representation, you immediately see that it means that this matrix must be 0. But this is diagonal matrix. All entries are diagonal. X is diagonal, D is diagonal, all of them are diagonal. So we have just n equations, and they are just equations of motion. So let me write them explicitly. So you see that this is some new system which was previously unknown. It is integrable, and comparing to Calogero-Moser system, we see two main differences. First, that now we have dependence on velocities, not only second time derivatives enter, but also first time derivatives and velocities. And another important difference is that here we have three-particle interaction. So three particles are involved, xi, xj, and xk. This sum is taken over all different indices. This notation means that I, j, and k are all distinct, from 1 to n. And in fact, this equation can be obtained as the limit eta to 0 from the deformed Rosenars Schneider model. Most probably, this system is not Hamiltonian. All attempts to find any Hamiltonian structure failed. So this is not most likely not Hamiltonian. But we can find equations of motion for this system. First of all, we note that this this matrix is traceless. This is obvious from the explicit form, because p prime is an odd function. So if you sum all diagonal terms, you get sum of p prime of xi minus xj, sum over all pairs, and this is 0. So from the Monakov's triple representation, it follows that the characteristic polynomial of the matrix L is conserved, is an integral of motion. We did this calculation, simple calculation, in case of deformed Rosenars Schneider model. So I will not repeat it. And the conclusion is that this characteristic determinant is integral of motion, and the equation of the spectral curve is the curve consists on such pairs z lambda for which this determinant vanishes. There are two problems, and from expanding it in powers of z, you can find integrals of motion explicitly. And the first two are as follows. again, this is a sum over all distinct indices. A problem for you is to prove that they are conserved by a direct calculation. So you can try to find the time derivative, and from these equations of motion, it is possible to show that this is zero. So you sum all these equations in I, then you get from this term you get this, and the problem is to prove that sum of this combination in I is zero. This follows from some identities for Weierstrass function. For example, there are identities of the following form. For each n greater than 2, we have the following identity. And we need to prove that these quantities are conserved. We need this identity for n equals 3 and 4. They can be proved using the standard method, which I explained earlier, to consider the left-hand side as a function of one of them, for example, of x1. Then it is an elliptic function in this variable, because Weierstrass function is elliptic. And then you should try to find what singularities this expression has, and to prove that all singularities cancel. So this is a constant, and this constant can be found by at some particular point when it simplifies. And what about elliptic? What about this spectral curve? It can be proved that it is rather obvious that the Lax matrix satisfies the following identity, that if you take the arguments with minus sign, you obtain transposed matrix. So the spectral curve has a holomorphic involution when the pair z lambda is sent to the pair minus z minus lambda. So when values of integrals of motion are fixed, this equation defines a covering of elliptic curve 2n with 2n sheets above the point lambda in elliptic curve. And it can be proved that the genus of this curve is 2n. And the last remark about this system is that it can be obtained from usual Calogero-Moser elliptic system in the following way. Consider, so we have particles on the line with pairwise potential given by psi function, and consider a system with even number of particles. So there are 2n particles. And consider configuration when the neighboring particles merge in pairs. So they stick together. So at this point, there are two particles, x1 and x2. And similarly, x3 and x4, and so on. Here we have x2n minus 1 and 2n. Two particles in one and the same point. Such strange configuration. Of course, it is singular, because this function has a pole when 2 points coincide. However, we can introduce some small parameter epsilon such that the difference between particles in each pair is epsilon, and tend epsilon to 0 at the end. In this way, it can be shown that this configuration destroys by flows, Hamiltonian flows in times with even index. So, for example, it is destroyed by the Calogero-Moser dynamics with respect to the standard Hamiltonian. However, if you consider dynamics with respect to H3 and flows with odd times, then these flows preserve such configuration. It is a rather complicated calculation because we have, at each step, we have many singular terms. When epsilon goes to 0, such terms diverge, and they cancel only at the very end of the calculation. And the result is that the dynamics of these pairs as functions of T3, so the Calogero-Moser dynamics in for the Hamiltonian H3 is exactly the same as these equations. Of course, this resembles the result which we discussed for deformed Rosenard-Schneider system. In that case, there were also pairs, but they were not singular. The distance between them was equal to eta. And if you considered the dynamics of the pairs as whole things, only half of the flows preserved such configuration. But this dynamics was the deformed deformed Rosenard-Schneider system. And now, as I said, these equations of motion, which are obtained as dynamics of poles for elliptic solutions to BKP, and BKP is obtained as eta, when eta tends to 0. And so this in each particles in each pair merge, and finally we obtain this singular configuration in Calogero-Moser model. Okay. And now let me pass to a more general hierarchy, which is called Toda lattice hierarchy. And so first we will introduce this hierarchy and then consider singular solutions, and we will show that the dynamics of singularities of these solutions gives the Rosenard-Schneider systems. This hierarchy is also called two-dimensional Toda lattice. The set of independent variables is larger than in KP hierarchy. So we have times T1, T2, so on. The same set as in KP, but also another set, T1 bar, T2 bar, and so on. And bar does not mean complex conjugation. This set of times is sometimes called positive times, because the index is positive. And this is called negative times, because sometimes they are denoted as T minus with minus K. And beside, there is also another variable which is called zeroth time, denoted by T naught, or will be denoted by X, because we will consider elliptic solutions in this X. Very often this variable is taken to be discrete, integer, just integer number. However, in solutions which we are interested in, this variable can be extended to any complex value, and the equations with respect to these variables are difference, not differential, but difference. So we can write it as some constant value plus eta times n, where n is integer. So this hierarchy is defined by two Lax operators rather than one. And they are Laurent series in shift operator, which is we will denote as exponent of derivative. So this operator acts to a function of x by shifts. So we have the following series with some coefficients uk. Series in inverse in shifts. This is shift to the right, and all these are shifts to the left. This is first operator, and the second Lax operator is it starts from the shift to the left, however with some non-trivial coefficient. Here we fix it to be 1, and here there is some function plus a series. And the hierarchy is defined by the following Lax equations. Bm are difference operators obtained by we raise the Lax operator to the power m and take the differential part. And similar equations for derivatives with respect to negative times. Where B bar is obtained from the second Lax operator by taking strictly negative part. For example, B1 is the shift operator of this form, this U0 coefficient, and B bar 1 is shift to the left with some function here. An equivalent formulation of the hierarchy is with the help of Zakharov-Shabat equations, which have the familiar form. And the other two equations for t bars and a mixed equation when one of these times is positive and another is negative. I will not write them explicitly. And or maybe just this. And when the m and n are equal to 1, then from this equation you get a system of the following form. Let me denote U naught by V. Then the system is as follows. And X is T1, T naught. The first equation, and the second equation is so we have two equations for two functions. The function v can be excluded from this system, and if you substitute for c, introduce a new function phi according to this formula, then you get an equation for this function phi of the following form. And this is the famous Toda, two-dimensional Toda equation. Two-dimensional because we have here two variables, which are sometimes called x and y, and are regarded as space variables. Original Toda equation was for the case when these two were equal, and so we had just second derivative in time on the left-hand side. The more general equation appears when they are splitted in two independent variables. So this is a famous Toda equation. And we are going to consider its elliptic, rational, trigonometric, or elliptic solutions of this equation as functions of x. And we are interested in dynamics of poles as functions of T1 and T bar 1. The Zakharov-Shabat equations are compatibility conditions for the linear system for some function psi, which is called a wave function. This function can be represented in the form of a series. It depends on spectral parameter. And here we have a series where xi's are functions of x, t, and t bar. And we will also need a dual psi function. So these pre-exponential factors go with minuses here. For example, the first equation of this system for psi looks like this. And our strategy will be to take the elliptic ansatz for V and the corresponding ansatz for psi, substitute them into this equation and cancel poles. In this way, you will obtain some system which eventually can be reduced to Rosenau-Schneider system. Let me also say some words about the tau function. The tau function is a function of x and the two infinite sets of times. And the integral bilinear equation for it can be written in the following form. This is the left-hand side, and on the right-hand side you have integral. This is a big counter around infinity, and this is a small counter about zero, around zero. Excuse me, here is -1. So here we have shifts in times t, and here the shifts are in times t bar. This should hold for all t bar and x prime, such that x prime minus x divided by eta is an integer number. The coefficients of the Lax operator can be expressed through the tau function. For example, the two simplest ones. I will not indicate explicitly the dependence on the times, only on x, which is shifted here. And the psi function also can be expressed through the tau function. One can introduce also, along with psi and psi star, one can introduce another pair of wave functions which are associated with expansion around zero. These two are associated with expansion around infinity. So we have minus 1 power here. And these two pair, they satisfy the same linear equations and are given by the following formulas. Of course, now I present only some sporadic, so to speak, formulas. because the systematic study of the Toda lattice hierarchy may take the whole semester. So there are only main formulas, probably without any visible logical connection between them. However, we need them, and more details you can find in the written notes of the lectures. And we will also need the following identity, which is obtained from this in the way similar to what we had for the KP hierarchy. We differentiate this identity, for example, with respect to Tm, and after that put all prime variables to equal to the variables without prime. Then you can obtain the following identity. Okay, we will probably stop here for today, and next time we will derive the dynamics of poles using all this technique. We will derive dynamics of poles of singular solutions to the Toda equation as functions of x, and dynamics in T1. And we will see that this dynamics is just the Rusinard-Schneider system.